and welcome to you all for this Infosys prize lecture series, which is in its 10th year, jointly organized by the Infosys and the Indian Statistical Institute, Bangalore Center. So welcome to the speaker of the day, Professor Ritabrata Munshi, who is the 2017 Infosys laureate. And also welcome to Professor Rajaram Bhatt, who is the professor in charge of the Theoretical Statistics and Mathematics Division of the Indian Statistical Institute. So some months ago, the Infosys Foundation asked us if we could organize this lecture series in our campus. Then I told them that we will be absolutely delighted because Professor Munshi is our colleague from the Kolkata campus of the Indian Statistical Institute. And more so, he was also a student here during his second years of master's in 2000. And I am particularly delighted because I was one of his teachers. So nothing gives me more pleasure than to be at the organizing end of this particular event. So I have been with the Infosys prizes from the inception. Gratefully, I am in the nomination committee, so I have been in this thing for 10 years now. And I was at the first award ceremony in when one of our colleagues, Professor Manindra Agarwal, was awarded the prize in mathematics in the first award ceremony. And one of the great surprises which came to all of us, including Professor Agarwal, was that the prize amount, which was announced as 5 lakhs when the prize processing began, at the award ceremony, it was announced as 50 lakhs. So it was an absolutely delightful way of recognizing the contributions of our scientists to this society, to say that the foundation has a tenfold increase of what they have initially announced. And the prize money, of course, has grown by years because of the increase in the corpus fund. And in 2017, one of the delightful moments for us is because 2 people from the Indian Statistical Institute were awarded the Infosys prize. Our director, Professor Sangamitra Bandyopadhyaya, and today's speaker, Professor Ritabrata Munshi. So I have a very delightful anecdote to share here. The institute is chaired by Professor Govardhan Mehta. And Professor Mehta suggested to us that in the council meeting, which is the highest governing body of the institute, we not only transact the matters of the institute, but also showcase the achievements of the institute. So then, with his direction, we agreed that in each council meeting, we will request one young colleague to come and present his scientific achievements to the council of the Indian Statistical Institute. And last year, in one of such meetings, I am very pleased that Professor Ritabrata Munshi was showcased as achievers of this institute, and he gave a presentation in the council meeting. But the main aspect of my story is that that council meeting actually was attended also by Professor Manindra Agarwal, who is a nominee of Indian National Science Academy to our council. And the council meeting also had Professor Arunava Sen, another Infosys laureate from our social sciences department from Indian Statistical Institute, Delhi. And of course, it had our director and this. So I was telling everybody, this is probably the only council meeting where we had 4 Infosys laureates present in the council meeting. So it has been a wonderful achievement for us to have so many people getting a distinction on behalf of the institute and generally making their mark in the field of sciences. So you have, of course, a very detailedly composed description of Professor Munshi's achievements in the announcement that we have circulated. So I'm not going to read it out. But I'm just going to add, in addition to everything, I also had the pleasure of listening to him as an invited speaker in the recently concluded International Congress of Mathematicians, which is a once in a 4-year event, and it was held in Rio de Janeiro this time. So I had actually another pleasure of listening to him very recently in this most prestigious mathematical event that takes place once in 4 years. So with this brief introduction, let me now request my colleague, Professor Rajaram Bhatt, to tell you briefly about the theoretical statistics and mathematics unit of division of this institute, which is, in my opinion, the flagship divisions of this institute. Thank you.
Welcome, everybody. Actually, I don't have much to say because it's mostly an ISA gathering, I guess, and our own students, and I guess they know about our division, StatMath division, right? But there are some Infosys representatives here, so I'll just say 1 or 2 words. Like ISA has a very long tradition of research in pure mathematics and statistics. Like you would know definitely SRS Varadan, the only Abel Prize winner from India, and is of course involved in the selection committee for this Infosys Prize Award. So then there are many other names. Like if you are not a mathematician, maybe you have not heard, but there are many distinguished names like K.R. Sarathi, Professor Rama Rajan, or statisticians like C.R. Rao. There is a long list of names. So ISA has a very good tradition of research in pure mathematics, applied mathematics, statistics, and so on. But there is, since Infosys is a private company, I would like to mention another point, that is like the research in ISI, means all this teaching research has been possible because of the research atmosphere. It's provided by the funding, right? The generous, very generous funding from the government, central government. But in recent years, they have been telling us, no, you should generate private funds. You should get money from private companies, which is not easy for us, right? In India, the private companies generally are not interested in research. But we are very happy that Infosys has instituted this prize and is looking into it. See, the thing is that, okay, the companies are interested sometimes if we are doing some research for them, some applied research. But the kind of research like Professor Ritabrata Munshi is doing, it's purely theoretical. So we do it because we enjoy doing it and we think it is important, it's fundamental, right? I mean, people have been working on primes, understanding primes, how to factorize primes, just for that sake, right? Just to understand them. But then there came this thing like encryption, public-private key encryption, where this factorization of numbers was crucially used. Even now it is being used, right? So a lot of this research, what we call pure research, gets used sometime later on. We don't know when it will, right? It might be many years after that you find some use. So just applied research cannot survive. There has to be pure research also together with that. So I don't know how we can convince the private companies that or the government that research needs funding, even the pure research. Like, we don't want to generate funds by increasing the fees of students, right? So we are looking at options, how we can get funds. So like, for instance, if the companies can organize, sponsor our conferences, we'll be very happy. But we don't know what we can give back to them immediately, because this kind of research goes on for years, and sometimes you find some use, but genuine uses, there are numerous instances. Like this is one thing I'm saying, the public-private key encryption, where you are using the factorization of numbers. But there are too many to count. You just have to look at the history to see that research gets used later on. So that is something which I wanted to say. Now, anyway, I don't want to stand in between you and Professor Ritabrata Munshi. Actually, some time back, we tried to get him here. I remember that I was trying to persuade him to join ISA Bangalore. He debated it for some time and then said no, for some personal reasons he cannot do that. But anyway, we are very proud that he is our colleague. But we are even more proud that he was our student, right? We are always very happy when our alumni achieve something. We are very proud of him. So let us listen from him. So thank you for just coming here.
So in a meeting like this, there is generally no vote of thanks, but I would nevertheless thank the Infosys Foundation, and particularly Ms. Swati and her team, and from the ISI, the employees of the institute, particularly Ms. Ashwini, who coordinated and made this event possible. Now we will have a brief movie on Ritabrata, followed by talk by Ritabrata. So I will request you to join the thing. And
my romance with mathematics started very early in my life. And I was like 7 or 8 years old, I stumbled upon this journal that my father used to keep, and it had this mathematical expressions which kind of attracted me. There was a mystery behind that I was not able to understand. Then I got this book on Rama Rajan. While reading that book, I got attracted to number theory. I think that was the beginning of the journey. It has been a long journey. It's very hard to imagine a life without math. One day, the way that Rama Rajan had influenced me, maybe one day I will be able to influence other kids to take up math and do research in mathematics. That would be fantastic. So I'd like to begin by thanking Infosys Science Foundation and ISI Bangalore for organizing this talk. So I'm going to talk about, as the title suggests, analytic theory of L functions. So that's something very technical. And I'm going to start around 400 BC. And at the last slide, I'll come to something that I did 2 weeks back. So I'm just going to cover like 2,400 years in this lecture. So Euclid was the first person to prove something about prime numbers. So the statement he proved that there are infinitely many primes. And we all know how to prove it. And even if you don't know how to prove it, you can prove it just now. It's very simple. But when Euclid did that, it was something very new. Okay, and but his method was not possible to generalize that much. So if you ask me, how do you prove that there are infinitely many primes of the form 5n plus 3? So these are primes in an arithmetic progression, right? 5n plus 3 is an arithmetic progression. Then it's very difficult to generalize Euclid's proof. Okay, or if you ask something much harder, like show that there are infinitely many primes of the form n squared plus 1. So there are infinitely many primes where you add 1 to a square, it gives you a prime. Okay, and it's still open. No one knows how to prove it. Okay. So if you can generalize Euclid's proof to do anything like that, that would be fantastic. But we have tried, it doesn't work, it seems. So like 300 years back, I guess, Euler found a new way of proving there are infinitely many primes. Okay, and this is how he proved it. So this is the picture of Euler. He introduced a series, 1 plus 1 by 2 to the power s plus 1 by 3 to the power s, etc., where he took s to be a real number larger than 1. And then you know that this series converges. It's something that we learned in our first year analysis course. And the fundamental observation that he made was that this series is also equal to this product, a product over prime numbers. So this series is related to the prime numbers. Okay, and that's just the fundamental theorem of arithmetic, right? And what happens is that this series diverges as you take s near 1, right? 1 plus 1 by 2 plus 1 by 3 diverges, as you all know. And that means that this product should also diverge when you plug in s equals to 1 in that product, right? And that will mean that there cannot be infinitely many primes. There should be infinitely many primes. So that is another simple proof of individual prime. And the main thing about Euler's proof is that you can generalize this, okay? And you can prove fantastic things using this idea. So in 1837, Dirichlet used Euler's idea to prove that there are infinitely many primes in any reasonable arithmetic progression. Okay? So if you look at an arithmetic progression a plus nb, where a and b are fixed numbers, a is less than or equal to b, and a and b are coprime, then there are infinitely many primes in that form. Okay? And the way he did that was to look at, so he introduced this what is called an L series, L is chi, and it's defined by 1 plus chi 2 by 2 to the power s plus chi 3 by 3 to the power s, etc., where chi is a character of the multiplicative group Z modulo B Z star. So I'm looking at the progression A plus NB, B is a positive integer. So I look at the group Z modulo B Z star and look at the invertible elements of Z modulo B Z, and that's a character. So that's a multiplicative map from the group to C star. Okay? And he looked at this series. So chi 2, chi 3, chi 4 are all complex numbers. They are all lying on the unit circle. And somehow he related this to the primes in the arithmetic progression. This is how he did. He made the same observation as Euler, that this L function or L series has a Euler product representation that is called a Euler product. It's a product over primes 1 minus chi p by p to the power s inverse. And he observed that if you look at the series 1 by p to the power s, p a prime, p congruent to a modulo b, so you're looking at the primes in the arithmetic progression, then that is more or less same as that sum over chi. So chi is running over all characters modulo b, chi a bar, because if you take the log, the product over primes become a sum, you expand the log and you pick the first leading order term, and that will give you the left hand side. Okay, so the left hand side is the leading order term in the right hand side. So that is related to that. So if you want to show that there are infinitely many primes in the left hand side, you have to show that the right hand side diverges. That was Euler's idea, right? So at least, so if you look at the sum on the right hand side, there are finitely many characters, so that sum over chi is finite. So we have to show that log ls chi is diverging for some s. Okay, so if you take chi to be the trivial characters, which takes 1 for all n's, right, then we know that it diverges, because it's the same as the, you're taking the zetafunction that Euler was looking at, and that diverges at s equals to 1, that we have already seen. So that particular L function diverges, and then he showed that the other L functions, if you look at L1 chi, it is neither 0 or infinity. So log of L1 chi is finite. Okay, and that showed that the right hand side is diverging when s tends to 1, and that proves that there are infinitely many primes in an arithmetic progression. Okay, as simple as that. Okay, so that was Dirichlet's idea. So that if you want to understand an arithmetic function is a function defined over natural numbers, which are usually multiplicative. So I'm not going to define it precisely here. The idea was to study an arithmetic function. You define this series n by n to the power s and try to understand the analytic properties of the series. Okay? So more you understand the analytic properties of the series, more you can say about the arithmetic function. For example, if you can show that the series diverges at some point, that will mean that a n is not equal to 0 for infinitely many n. Okay? So that is the simple idea that Dirichlet was using. Okay? So now let's turn. So that was the origin of the theory of L function. So Dirichlet was the first person to define L function. And before that, before him, Gauss in 1796, he was just a teenager at the time. He was looking at the tables of prime numbers and trying to find pattern in the prime numbers. So he defined this function pi x, which counts the number of primes less than x. Okay, and he looked at some logarithmic table, and he predicted that this asymptotically this function pi x should behave like x by log x. Okay. So now we call this PNT or prime number theorem, because today we know it. At the time in 1796, when Gauss made this conjecture that this is pi x is x by log x asymptotically. And that was a central problem back in 18th century, back in 19th century, early 19th century. So Riemann realized that so if you want to prove the prime number theorem as conjectured by Gauss, you have to understand the function defined by Euler more precisely. So he looked at the same function that was defined by Euler, zeta s, but he made a significant progress by looking at this as a function of complex variable s, not a real variable. So Euler just looked at zeta s for s greater than 1, but Riemann realized that you have to understand the primes, you have to define zeta s for s complex numbers. okay, and introduce the complex analysis. So S is going to be sigma plus IT, where sigma is the real part and T is the imaginary part of S. And the first thing he showed was that I think there are no proofs in Riemann's papers, but it's generally believed that he knew how to prove all this statement. So one of the statement was that the zeta S makes sense. It makes sense for any sigma larger than 1. So if you look at the right hand plane, sigma greater than 1, it is converging. So it gives you an analytic function, but it also continues analytically. Okay, so those of you who know complex analysis will understand what I am saying here. So zeta S has an analytic continuation, except there is a pole at S equals to 1. So at S equals to 1, you cannot define the value zeta S because it's going to blow up and become infinity. But at any other point, you can define zeta S, okay, in a reasonable way. For example, zeta 0, which is apparently 1 plus 1 plus 1, 1 added infinitely often, should give you minus 1/2. And zeta of minus 1, which is the sum of all positive number integers, 1 plus 2 plus 3, etc., should give you the value minus 1/12. Okay? Okay, so this is just for those who don't know complex analysis, but it's just, of course, what I'm saying here is just meaningless because that's going to be infinite anyway. Anyway, so how was the distribution of primes related to zeta? So Riemann came up with this explicit formula by studying the zeta function. So on the left hand side, you have the sum over prime numbers log p. P is a prime and p to the power k is less than or equal to x, where k is from 1 to etc., taking all integer values. And that is equal to x minus x to the power rho by rho, a sum over rows, where the rows vary over all beta plus I gamma, where beta is taken between 0 and 1, and rho is 0 of the Riemann zeta function. Okay. So zeta is now known as the Riemann zeta function, minus log 2 pi. Okay. So that was Riemann's main formula in his paper. So on the left hand side, you have a sum over prime numbers, and on the right hand side, you have a sum over the zeros of the Riemann zeta function. Okay, this is an explicit relation between primes and the zeros of zeta function. And so if you understand how the zeros of the zeta function are distributed, then you will know something about the prime numbers. Okay? So in particular, if you want to prove the prime number theorem, so if you want to prove that pi x is like asymptotically x by log x, what you need to prove is that the zeta function, zeta 1 plus it, is not equal to 0 for any t. So as you know, that for sigma larger than 1, the zeta function converges absolutely, and there is no 0 of the zeta function in the region sigma greater than 1. But if you are able to prove that it's not vanishing even if you are very near at the edge of the strip, right, then that is 1 plus it is the edge of the strip, then you are done. We have a proof of prime number theorem. Okay? And that was finally proved in 1896 by Adamard and Dirichlet. Okay? And so in exactly 100, it took 100 years to prove the prime number theorem. All right? But Riemann went much further. So he conjectured that in fact the Riemann zeta function, the zeta function does not vanish in the half plane sigma greater than 1/2. Okay? So half is far away from the edge of the critical strip. Okay? So the edge is the line passing through 1, and you are saying that it's not vanishing at any point where sigma is larger than half. Okay? That came to be known as the Riemann hypothesis, which is perhaps one of the most, if not the most important problem in modern day mathematics. Right? And if you prove that it's not vanishing, then if you use the explicit formula of Riemann, then you'll get a very precise form of the counting function pi x. So you'll get that pi x is exactly equal to this integral dx by log x with base e plus an error term of x to the power 1/2 plus epsilon. Okay? So what Gauss had conjectured was just the first term in this series. If you integrate 1 by log x, the first term is like x by log x, and that was a leading term. But this is much more precise. So it says that is pi x is exactly that with an error of size x to the power 1/2. So if we write x in using digits in a decimal expansion, if x has 100 digits, then a square root of x will have 50 digits. So the error is much smaller than the number, counting number function. Okay, so that was the origin of L function. So I described the idea of Euler and how Dirichlet used the idea of Euler to prove infinitude of primes in arithmetic progression, and how Riemann realized that to understand L functions better, you have to understand it as a function of complex variable rather than real variable. Okay, so now I am going to define, or not really define, give some examples of L functions. Two examples we have already seen. One is the Riemann zeta function, right? It's given by that series 1 by n to the power s, but it's also given by the Euler product 1 minus 1 by p to the power s inverse. Okay, for at least for s equals to sigma plus it and sigma larger than 1. Okay, it's absolutely converging. Both the series and the product are absolutely converging. The main thing that Riemann proved that it has analytic continuation except a pole at s equals to 1, and it satisfies a functional equation. So the functional equation says that the value of zeta at s is related to its value at 1 minus s. Okay, so the point 1/2 is kind of a point of symmetry, and if you reflect s at 1/2, you reach the point 1 minus s, and the values at s and 1 minus s are related. Okay, so and that the precise relation is given by that. So you have to multiply by some gamma function, gamma is by 2 by pi to the power s by 2, and then we have this precise functional equation. Okay, so these are the main properties of the Riemann zeta function that Riemann wrote down. And the good thing is that the same thing holds for the Dirichlet L function. So if you look at L is chi, it's given by Dirichlet series, that's called the Dirichlet series, chi n by n to the power s in 1 to infinity. It's also given by the Euler product of primes 1 minus chi p by p to the power s inverse. Okay, and it both the series and the product converges absolutely for sigma larger than 1. They extend to an entire function except when chi is a trivial character, when it has a pole at s equals to 1, a simple pole. Okay, and again it has a functional equation, but now the functional equation relates the value of L s chi with the value of L 1 minus s chi bar, okay, where chi bar is the conjugate, complex conjugate of chi. So you don't really have a relation between L s chi and L 1 minus s chi, but L s chi and L 1 minus s chi bar. Okay. Okay, so these are the fundamental properties which define an L function. So the one is it's given by a Dirichlet series, it's given by a Euler product in some half plane, and it extends to an entire function with a possible pole at point s equals to 1, and it satisfies the functional equation. So these 4 properties define an L function. Okay. Okay, so let's give another example of an L function. So we have already seen Riemann zeta function, Dirichlet L function satisfies the properties. So this is something of something more complex than those two. So you look at this series delta z, which is given by this product q times 1 minus q to the power n to the power 24. So this is something which goes back to Jacobi, all right, and you can also expand the product, and tau n's are defined as the coefficients in the product in the series. It's tau n times q to the power n, where you are taking q to be e to the power 2 pi I z, and z is on the upper half plane. So if you take z in the upper half plane and q to be e to the power 2 pi z, you can show that that product and the series are absolutely converging. They make sense. Okay. And the nice property, so this delta is a function on the upper half plane, okay, and it's a holomorphic function on the upper half plane. And it satisfies this marvelous transformation property, that if you look at delta of az plus b plus divided by cz plus d, then it is exactly cz plus d to the power 12 delta z, okay, for any abcd integer matrix in SL to z. Okay. So it has this many symmetries hidden inside this function delta z, and the thing is that there are many functions which satisfy properties like this. okay, and those are called modular forms. Okay, so they are holomorphic functions on the upper half plane, which has a group of symmetry, which will be a subgroup of SL to Z of finite index. Right. So Ramanujan was very interested in this type of functions. So he was particularly interested in those numbers tau n defined in the series, which are called the Fourier coefficients of the function delta Z. And he made two fundamental conjectures about those tau n just by looking at studying the sizes of tau n. So he conjectured that this function tau is multiplicative. Tau mn is tau m times tau n if m and n are co-prime, and that the size of the tau p, where p is a prime here, is bounded by 2 times p to the power 11 by 2. Okay. So, so the first thing is saying that these taus are an arithmetic function, and the second thing is saying something about the growth of this arithmetic function. Okay. And there is a conjecture. So this were proved later. The first conjecture was proved, I think, just a year after Ramanujan made the conjecture. So it's not that difficult to prove. But Hecke later gave a different proof of this fundamental relation, and his proof is more fundamental in the sense that he really understood the structure behind it. So he introduced what are called Hecke operators, and Hecke operators is something which plays a very important role in the theory of modular forms. Whereas Model proved the first conjecture just a year after Ramanujan proposed it, but his proof was something different. The second conjecture was proved much later in 1970s by Pierre Deligne, and the conjecture. So both these conjectures can be generalized to what are called to general modular forms and or automorphic forms. The first conjecture is proved for all of them. The second conjecture is proved only for modular forms, but it's not known for general mass forms or automorphic forms. Okay, that's the famous Ramanujan conjecture, which is one of the most important conjectures in modern day mathematics. Right? Okay, so as I said, the delta is an example of a modular form. It's also a cast form for those who know this. It's of weight 12 and level 1. And if you define tau naught n by normalizing it by dividing by n to the power 11 by 2, which is the size of tau p, then if you define this series tau naught n by n to the power s, then the first conjecture of Ramanujan says that this has a Euler product, right? The multiplicativity of tau implies that this series can also be written as a Euler product. Okay, and the second conjecture of Ramanujan says that it converges absolutely for sigma larger than 1. And later Hecke proved that this actually extends to an entire function, and it satisfies this functional equation. Okay, so that's my definition of an L function. So the modular forms also give rise to functions which satisfies the standard properties, which are also satisfied by the Riemann zeta function. So these are called modular form L functions. Okay, so the modular forms, and delta is one example of a modular forms, are in fact related to what are called some special representations of Lie groups, right? And which are called automorphic representations of Lie groups. And for any automorphic representation pi for a Lie group, it's enough to look at the general linear group GLD AQ, where AQ is the Adels over the field of rationals. And then the automorphic form splits as a product of pi p, and then you can attach an L function to that. It is given by this product over p prime ls pi p. Ls pi p are the local L factors, which are defined in this way: 1 minus alpha I p p to the power minus s inverse. Okay, and you have to define the gamma factor in this way. So the point is that we have this Riemann zeta function, the Dirichlet L functions, which were classical, and then in the beginning of 20th century, people were getting new types of L functions. So functions which are behaving like Riemann zeta function and Dirichlet L function, but which is something slightly complicated, right? Because if you look at the Euler product over here, for for Dirichlet L function, it was just 1 minus chi p by p to the power s inverse. And but here you have a quadratic term, 1 minus tau naught p by p to the power s plus 1 by p to the power 2s. Okay. The point is that the Dirichlet character is completely multiplicative, but if you look at tau naught p square, then it is not tau naught p square. Tau naught of p square is not tau naught p square. Okay. So it's not completely multiplicative. It satisfies a recurrence relation of degree 2, and that's why you get a Euler product of degree 2. Okay. So these are modular forms L functions are examples of L functions of degree 2. And if you are looking at automorphic forms of general linear group GLDAQ, then you get L functions of degree D, okay, which is something much more complicated. But anyway, these L functions also satisfy the same properties. They are given by a Dirichlet series and a Euler product converging absolutely in a half plane and extends to an entire function and satisfies functional equation where the value at Ls pi is related to L of 1 minus S pi tilde, where pi tilde is something called the contragradient representation of pi. Okay, so we have a huge class of examples of L functions which behave in a similar fashion as the Riemann zeta function. Okay, and that's something good. So if in mathematics we often try to do this thing that if you have a particular object, we try to find out objects which are very similar to that. Okay, and it helps us to understand the particular object that we started with. Okay, so if you are interested in the Riemann zeta function, so the idea is that instead of just looking at the Riemann zeta function, you look at the whole class of L functions that is around, and from that maybe you can get some information about the Riemann zeta function at the end. Okay. All right, at this point let me define something called the conductor of the automorphic form phi, which is given by this q pi times 1 plus mu y plus I to the it, right? So let me tell what q pi is. So q pi is something that appears in the functional equation q pi to the power s by 2 over there, and the mu y's are the parameters which appear in the gamma function over there, okay, and the factor at infinity. Okay. So this c pi t is called the conductor of pi, and this is a measure of the complexity of the L function. Okay. So later we'll be interested in understanding the size of the L function beyond the region of absolute convergence, and then you may ask, so if you are interested in understanding the size, you have to define a scale with respect to what you want to understand the size of the L function. So the answer is we want to understand the size of the L function Ls pi with respect to the conductor. Okay? So if you give me an automorphic form, I can very easily compute the conductor c pi t, that's the formula, but it's very difficult to compute the L function. Okay, so there are other sources of L function. One is elliptic curves. So if you look at this equation y square equals to x cubed plus ax plus b, where a and b are integers, you have to choose a and b avoiding some pathology so that it's not singular. And then for every prime p, let ap be 1 plus p minus the number of solution of that equation modulo p. Okay, so that's basically the number of primes, number of rational points in that curve. Y square equals to x cubed plus ax plus b is a curve. So number of solution of that rational points on that curve modulo p. That's that last number of points in EFP. Okay, so if you have a straight line, then the number of points on the straight line modulo p will be p plus 1 if you count the point at infinity. And this is kind of counting the, is a deviation from being a straight line. So elliptic curve is not a straight line, so it's not 0, okay, most of the time. So then you define the L function LSE by this product. So APs are bounded by root p, that was proved by Hasse in his thesis. And if you normalize AP by dividing it by root p, then it becomes of normalized, so it's become of size 1 more or less. And then if you define this Euler product, 1 minus AP by root p by p to the power s. So again, it's a degree 2 Euler product, as you can see. So that's called the Hasse, it's called the Hasse L function attached to the elliptic curve. And it was conjectured by Hasse and Wei that this L function actually extends to an entire function. Okay. And it was conjectured by Tanya Mashimura that this L function is actually modular, in the sense that there will be a modular form such that the L function of the modular form that I defined in the previous slide matches with this L function of the elliptic curve. So saying that an elliptic curve is modular is saying that the L function of the elliptic curve is actually the L function of a modular form. Okay? And a little more than that also. Okay, so so we know about Hasselbalch conjecture and Tanya Mashimura due to the work of Andrew Wiles. The main conjecture that still remains open in this field is that the Bartsch-Sunyatin-Dyer conjecture, which says that the rank of the elliptic curve EQ. So if you look at the rational points, if you look at the rational solution of the equation y square equals to x cubed plus ax plus b, that forms an abelian group, okay, and that is a finitely generated abelian group. That was proved by Mordell long back. And as you know, for any finitely generated abelian group, there will be a torsion part, which is finite, and there will be a free part. Okay, so there will be some copies of z sitting inside it, and the number of copies of z sitting inside it is called the rank of the elliptic curve. And Bartsch-Sunyatin-Dyer conjecture says that the rank of the elliptic curve is equal to the order of vanishing of the L function at the central point. Okay, so let me say that usually people, if you go to genuine person working on elliptic curves, he will not divide AP by root P, so his central point will be at 1. So he'll say that the rank is the order of vanishing at 1. Okay, for me, all the central points are at half. Okay, for analytic number theories, the functional equations are always like s going to 1 minus s. For algebraist or geometers, it's different. Anyway, so that's another. We saw that Riemann related the non-vanishing of the zetafunction with prime distribution of prime, and Dirichlet related the non-vanishing of the LSK, the Dirichlet L function at some point, with primes in arithmetic progression. And the Bartsch-Sunyatin-Dyer conjecture relates the vanishing of that L function at the central point with the rank. Okay, a consequence of that is that if you know that L function vanishes at the central point, then there should be infinitely many points on the elliptic curve. Okay, and that is still open. All right, as I said, Wiles showed that LSE is modular, and as a consequence, one obtains Fermat's last theorem, FLT. It's a well-known story. And there is another problem which goes back to ancient Greeks. It's called congruent number problem. Here's the definition of congruent number. So an integer, positive integer, is called a congruent number if it's an area of a right-angled triangle with rational sides. Okay, so we know that 3, 4, 5 that forms sides of a rational of a right-angled triangle, and if you compute the area of that triangle, that is 6. So 6 is a congruent number. Okay, and 5 is also a congruent number, but the right-angled triangle corresponding to 5 is doesn't have integer sides. Okay, you have to allow fractions. So and you can show that 4 is not a congruent number, for example. You know that. So the problem is find all the congruent numbers. Okay. Okay. So how is this related to elliptic curves? Okay. So if so, what we are looking for here is we are looking for rational numbers a, b, c, so that they form a right-angled triangle. So that means a square plus b square equals to c square, and the area should be n. So ab by 2 equals to n. Okay. So we are asking, so given an n, whether we can find a, b, c rational numbers satisfying this two equation. Okay. And you can eliminate one of the equation, and you can see that that is same thing as saying that y square equals to x cubed minus n squared x has a rational solution xy with y not being 0. Okay, and that is an elliptic curve. Y square equals to x cubed minus n squared x is an elliptic curve. And so saying that n is congruent number is same thing as saying that this elliptic curve has infinitely many has a rational solution with y not equal to 0, and it's very easy to show that there are no torsion points except that, so it has infinitely many rational solutions. So n is a congruent number if En has infinitely many rational points, and that is the same thing as saying by Bartsch-Sunyatin-Dyer conjecture that if the L function vanishes at half of En, then n is a congruent number. So this is a way to determine when an integer is a congruent number. And now you may ask how to determine whether an L function related to En is vanishing at 1/2 or not. There are ways to do that using quadratic forms, okay, but I'm not going into that. Okay, so this is another example where the values, analytic properties of L functions are related to interesting arithmetic problems. Okay, so what are the main conjectures in this value? Okay, one is, so this is a very broad conjecture due to Langlands, called Langlands program, which says that all L functions that you ever encounter in your life are going to be automorphic. For example, the L function that arises from elliptic curves is automorphic, same thing saying it's modular. That is the Taniyama-Shimura conjecture. So it's a special case of this. Okay, and the BSD conjecture, as I said, stated that the rank has to be equal to the order of vanishing. And that is one way of looking at the BSD conjecture is that it's an analog of the local global principle. So if you have studied quadratic forms, you know that there is a local global principle. So if you are given a quadratic form and you want to see whether there is a rational solution of that quadratic form, it's enough to look at each prime and check whether there are solution modulo each prime. And if you're lucky and if you have solution modulo each prime, then you have a rational solution. So that's a local global principle. From local mod P, you can say something about rational. Okay? And this is because the L function here, LSE, is defined by local data. So you're looking at these numbers AP, which are defined by counting the number of solutions modulo P. Okay? So the right-hand side is something coming from the local data, and the left-hand side is something from the global data, right? So it's a local global principle in that way. Okay, but of course the main conjecture in the analytic theory of L function is the grand Riemann hypothesis, which says that for any automorphic L function L is pi, all the non-trivial zeros should lie on the central line 1/2. Okay? And so a consequence of the grand Riemann hypothesis is the generalized Lindelof hypothesis, which says that the size of the L functions cannot grow too fast. Okay? So as I said, that to make a sense of this, we have to know, we have to have a scale, and the right scale is the conductor. So again, that's the definition of the conductor. And so the generalized Lindelof hypothesis says that L12 plus IT pi is bounded by this conductor to the power epsilon for any epsilon positive. So if you give me epsilon positive, which may be very small, like 1 by a billion, then it says that there is a constant C depending upon that 1 by a billion, such that the L function is bounded by the constant times the conductor to the power 1 by a billion. Okay? So that's a generalized Lindelof hypothesis, and that is the consequence of the grand Riemann hypothesis, but it by itself is very important. All right. So before going to the next slide, let me point out that in the definition of conductor, there are a few different parameters that play a role there. One is the q pi, which is related to the level of the form. Okay. So if you're looking at a Dirichlet function, then q pi is the modulus of the character chi. Okay. There is a t aspect, okay, t to the power d, because there are d many copies of t hidden inside that definition of conductor. So if you're looking at the Riemann zetafunction, it will be just t. If you're looking at modular form L function, it will be t squared because it's dp2 and all that. And then there is a depth or spectral aspect hidden inside this formula, which are these numbers μ-wise. Okay, so those are related to the weight of the modular form or the eigenvalue of the Laplace eigenvalue of the mass form, if you know what mass forms are. Okay, so so the conductor has three different parameters. So it's like a cube which has a length, breadth, and height thing. So level is the length, t is the breadth, and the spectral aspect is the height type of thing. And if you want to bound the L function, you can forget two of the things and just try to bound it in one dimension. Okay, so you may be interested in the level only, and then you want to get a good bound for the L function in terms of the level, which may not be that good in terms of the t aspect or in the spectral aspect. Or you may be interested in the t aspect and you want to get a good bound in the t parameter, but you don't care about the level parameter or the spectral parameter. Okay? So this depends upon the question that you're looking at. Okay? All right. So now let me come to something technical over here, the subconvexity problem. So this is something that I am working on, and this is related to bounding the values of L function. Okay? All right. So as I said, the grand Riemann hypothesis implies that the L function can be just like the conductor to the power epsilon. But in general, the best we can do is that we can show that the L function is conductor to the power 1/4 plus epsilon. Okay? So that's called the convexity bound, and it follows from the functional equation, which is generally known in general for all L function. Okay? So that's kind of an easy bound for L function. But if you have some application in mind, it often turns out that the bound that you need has to be little better than the convexity bound. Okay? So if you get the trivial bound, it's of no use, but if you get something non-trivial, that gives you the application that you had in mind. Okay, I'll come to that. So the subconvexity problem is about breaking this barrier of 1/4. So you are trying to find a delta so that the bound is c to the power 1/4 minus delta, with delta positive. Okay, and again you can split it up into 3 different aspects. Okay, so here are 2 example applications of subconvexity. One is Hilberts 11th problem. So the Hilberts 11th problem says that if you have a number field, so number fields are finite degree extension of the field of rational numbers, and if you have a quadratic form, say in n variables, it's an n-array quadratic form Q over the number field, then you ask which integers in the number field or the number ring are represented by this quadratic form. Okay, so it's a very general question, which was first asked by Gauss long back, and now we know our complete solution to this problem. The Ziegel's mass formula, so that's something I'm not going to explain here, is plays the crucial role, and it answers the it solves the problem in most cases, except one case which corresponds to Q being positive definite ternary. So it's a 3-variable quadratic form which is positive definite, in which case the Ziegel's mass formula doesn't work. Okay? And in that case you need a subconvex bound for certain L function, L half pi twisted by chi, where pi is the GL2 form over the number field F. Okay? So this was finally done by Cogdell, Piatowski, Shapiro, and Sarnath for F totally real. So that's an interesting application of the subconvexity. And here is another interesting application of subconvexity, which is related to physics. Okay? So this is called arithmetic chaos, arithmetic quantum chaos. So you look at, so H is the upper half plane, and you mod it out by SL to Z. So that gives you the modular curve, gamma naught 1. It's something simple, it's just a sphere, as you know. And let F be a cusp form of level 1, so it's like the delta of weight k. So delta was of weight 12, and now I'm looking at cusp forms of general weight k. Okay? And then you can define a measure on this space x naught 1, and the measure is defined in this way. So you take absolute value of fz square divided by the Peterson norm, okay, and multiply by y to the power k dx dy by y square. Okay. So this gives you a probability measure on x naught 1, and for every f you are getting a measure, and the question is, as k goes to infinity, what happens to this measure, whether it gets uniformly distributed or not. Okay, so that was the quantum unique ergodicity conjecture, which said that it indeed gets uniformly distributed with respect to the hyperbolic measure. Okay? And to prove this, so there is a formula due to Watson which relates this to the subconvexity problem of what are called the symmetric square L functions, sim square f, where f is the same f over there, and sim square f twisted by g, where g is another modular form. Okay, that's called the Rankin-Silber convolution. Okay, so to prove this unique ergodicity conjecture, you have to prove subconvex bound for these two types of L function. The first one is a GL3 L function. F is GL2, but when you take the symmetric square, it gives you a GL3 degree 3 L function. And the next one, same square F cross G, is a degree 6 L function. It's a GL3 cross GL2 Rankin-Selberg L function. Okay? And you need to get weight aspects of convexity for this 2 L function to prove this conjecture. There is also a level aspects of problem in quantum inequality. So in this case, you'll be fixing the weight. Say you fix the weight to be 2, and you vary the level, right? So you define gamma naught q, the modular curve, h by gamma naught, x naught q is h by gamma naught q, where gamma naught q is a congruence subgroup where we are looking at A, B, C, D, where C is divisible by q. Okay? And then, so this gamma naught q sits inside SL to Z, so that gives you a projection map from gamma naught q, x naught q to x naught 1. All right? So if you have a measure on x naught q, you can push it forward and get a measure on x naught 1. So now if you start with the cast form of weight 2 of level q, that gives you a measure on x naught q a priori, but then you can use the projection to give a measure on x naught 1. And now as f varies, or as q tends to infinity, you are getting more and more measure on x naught 1, and you want to see whether there is a pattern in the distribution of that. And that was again conjectured to be converging weakly to the uniform measure. Okay? So that was also the level aspect quantum inequality. And it also will follow if you know the level aspects of convexity for the symmetric square and symmetric square cross G L functions. Okay, so that's so these are some of the very interesting application of subconvexity problem. All right, so here are some examples of subconvex bound. That is not 1992, that should be 1922, probably, yeah. It goes by, I think it's 1920. I don't know why I wrote 1992. It was done by, the first subconvex bound was proved by Hermann Weyl, Hardy, and Littlewood, but none of them wrote it down. So it was later written down by Landau. They proved a subconvex bound for the Riemann zeta function. Zeta half plus it is bounded by t to the power 1/6 plus epsilon. Okay, 1/4 plus epsilon is the trivial bound, convexity bound, and they improved it to 1/6 plus epsilon. So that is almost like 100, I think 99 years back. So what do we have now? We have this result by Bourgain, where he proved that this is bounded by t to the power 1/6 minus 1 by 4 plus epsilon, right? So the Lindelof hypothesis will be just t to the power epsilon, right? We are trying to move towards that. So we are trying to kill that exponent 1/6, and we are in the last 100 years, we have reduced from 1/6 to 1/6 minus 1 by 84. Okay, so that's a good progress, right? And so this is another example of subconvex bound due to Burgess from 1962. So that's more than 50 years back, and he proved this bound in the level aspect for Dirichlet function. So if chi is modulo b, he proved that it's bounded by b to the power 3 by 16 plus epsilon. So again, b to the power 1/4 is a trivial bound, and he improved it by 1 by 16, and this is still the record. Okay, and this is a record because of very fundamental reason in analytic number theory. So if you can break this bound, then you are really doing something very fundamental in analytic number theory, okay? And that will mean that you can make progress in other problems as well in analytic number theory. In 1982, Anton Good, he was the first person to prove anything for GL degree 2L function. So he proved the T aspects of convexity for modular form L function. He proved that it's bounded by t to the power 1/3 plus epsilon. So in case of modular forms, t square is the conductor. So 1/4 of t square, t to the power half, is a convexity, and it's t to the power 1/3. So this is like the Weyl bound in the GL2 case. So these are the more or less what I call the classical results in this field. Okay, so let me just briefly explain how these things are proved. So this is called the moment method. So suppose you want to prove a subconvex bound for an L function L half pi naught. Okay, so then what you do is you search for a family. Right? You search for a family which contains pi naught. So pi naught is an automorphic form, maybe a Dirichlet character, or maybe T, whatever it is. Then you search for a family F such that pi naught is inside that family F, and then you estimate the second moment. So you compute the L half pi absolute value square and pi summed over F. Okay, and now if you have a good bound for this moment, then you can drop all other terms and return pi naught and get a bound for L half pi naught. Okay, that's the idea, right? L half pi naught will be bounded by mf to the power 1/2. Okay, so that means that if you want to, so mf will be at least of size f, right? The value of f is the size of the family f. So all the L functions are at least of size 1. Okay, it cannot be trivially small if you, right? So mf cannot be better than the size of the family. So to get something subconvex, because you're getting the bound mf to the power 1/2, you need your size of the family to be the conductor to the power 1/2 minus delta, right? Because you're trying to beat q pi naught to the power 1/4. So the size of the family cannot be too big, right? On the other hand, what you will be doing is you'll be using approximate functional equation or something like that to approximate the value L half pi by a Fourier expansion, and then you'll open the absolute value square and try to do the sum over pi. Okay, something like this is called the trace formula. Okay, and when you do the trace formula or orthogonality relation, then there will be this diagonal popping up when n equals to m. You cannot get cancellation in this. That is the size of f, and you want to prove that it's otherwise small. Okay, so a trace formula is very strong if the size of the family is very big. Okay, so what you are trying to do is you are trying to embed pi naught in a family which is not that big. It cannot be bigger than square root of the conductor, but it cannot be too small. Otherwise, the trace formula will not be strong enough. Okay, and the question is, if you're give me a pi naught, whether I can get a family of this type or not. And most often, you cannot. Okay, and in case of GL1, degree 1 L functions, you're lucky you can get something like that. In case of degree 2, what happens often is that you are stuck at the boundary. You get a family which exactly matches square root of the conductor. Okay, so that's the irony. And when that happens, since we are clever, we know how to get past that. So if we are at the threshold, we know that the bad thing that we were doing is just dropping all the terms and just picking one of them. So why don't we just introduce a weight that will give more weight to the particular term that we are picking, okay? And in that way, you can beat. So usually you get a family which is exactly the size of the square root of the conductor, which is not a very bad case, because in that case, you can introduce weights which are called amplifier, and using amplification technique, you can get subconvex bound, okay? But when you move to GL3, even getting a family whose size is exactly matching the square root of the size of the conductor becomes difficult, and no one has ever found such a family, right? But the amplification technique worked, and worked very well for nearly 30 years, and these are examples of results that people got using amplification technique. The technique was invented by Friedlander Ivanich back in 1992, and as you see, a lot has been proved. Okay, and in 2010, Philip Michel and Akshay Venkatesh, they got a very different approach. It's called the period approach, and using that, it's a very general approach. They proved a subconvex bound for all L functions, or GL2 L function, or GL2 cross GL2 L functions. Okay. Except the thing is that they don't make delta explicit in their paper. But if you really go through their argument, you can try to make it explicit. It may not be that good, but you should also know that amplification plays a role in this approach also. So if the amplification technique is not really working in the basic cases, this may not work also. Right? So that was the story until 2010. People were stuck at degree 3. So the degree 1 was solved, the degree 2, degree 1 was classical, and where degree 2 was solved in various aspects, and GL2 cross GL2 were solved in some aspects. But we were stuck at degree 3. Okay? The problem, as I said, that for higher family, it is difficult to find the right family, higher degree. Okay? And hence, the amplification technique doesn't seem to work. So one needs a new approach. And here is a new approach. Okay? So the approach is try to understand the harmonics hidden inside the problem. Okay? So suppose you are trying to get a subconvex bound for L half plus IT delta. So delta is fixed, is the modular form attached to the discriminant, right? And t is varying. As t goes to infinity, we want to get a suitable bound for this. Then the approximate functional equation boils down this problem to studying this sum, tau naught n to the power it, where this size of small n will be like capital N, and the capital N will go up to square root of the conductor. The conductor here is t square, right? So capital N goes up to t. Okay? And the subconvexity problem says that you have to get cancellation in this sum. Okay? So tau naught n's are the Fourier coefficient or normalized Fourier coefficients of the form, and you have n to the power it. So tau naught n is oscillating, and n to the power it is oscillating. Okay? And the problem, since you are in Indian Statistical Institute, it's asking whether something about the covariance of two. You can think of them as random variables, and you're asking whether the covariance is small or not. Okay? So the idea is just why don't you just separate the oscillation of the Fourier coefficient from the oscillation of n to the power it. Okay? So you introduce a new variable m, and write the sum as tau naught n m to the power it. Delta nm is 1 if n equals to m and 0 otherwise. So that's the diagonal symbol. And then try to use some expansion of this delta nm. Okay? So here is an expansion, what's called Riemanns Formula. So it's a version of circle method. There's the Fourier expansion delta nm. And using this expansion, if you plug in this expansion of delta nm in this sum, you get Sn gets transformed into that. And then, here you can see that tau naught n is completely separated out from m to the power it. Then you can try to use some summation formula for n and the summation formula of m. The summation formula of m will be the Poisson summation formula for n, because there are Fourier coefficients involved. Those will be the Voronoi summation formula. So if you know what they are, try to use the summation formula. And then you'll be almost near the boundary, and then you do Cauchy to get rid of the involution, because there are only 3 sums there. You have already used summation formula in 2 of them. The other sum is too difficult to execute. So you do Cauchy to get rid of that, break the involutory property, and apply Poisson one more. Okay? So this is the main idea, and this is the template. Okay? And it works, okay, like a miracle in many cases. Okay, and so there are different, as I said, there is an interpretation of this in terms of basis. So what the sum that we're looking at is like an inner product of this vector of tau naught n's and n to the power it. And now the circle method, what circle method does is it computes the inner product of tau naught n with a basis vector v and n to the power it with the dual basis vector, and then you have to sum over the basis. Okay, so there are certain tricks that you have to, introduce in this template. One is called the conductor lowering, because the direct application that I just wrote down will not work really. We have to be a little clever at some places, and this is a crucial ingredient. And the other thing that you need is you have to, depending on the problem, you have to introduce different expansions of the delta. Okay, so in the last problem, I used the Klostermann's expansion of delta, which was in terms of exponentials. But there are other expansions of delta, okay, and that those usually come from what are called trace formula. So here is an example of a trace formula. It's a classical Peterson trace formula. where f's are the modular forms and lambda fn's are the Fourier coefficients of modular form, and SIMN is the Klosterman sum. So delta nm can be written as the Fourier coefficient in terms of Fourier coefficients of modular form and Klosterman sum, and that is that gives another expansion of delta nm, which I call the GL2 delta method. So here delta nm is written in terms of GL1 harmonics and GL2 harmonics. Okay, and these are some of the results that I have got so far, and there are other people who are also working on this, and they're also getting interesting results. So first, as I said, we got stuck with degree 3. So here are some examples of subconvex bound for degree 3. So the first one is the T aspect subconvex bound for degree 3. So T to the power 3/4 is the trivial bound, and it's 3/4 minus 1 by 16. So the first bound. Again, m to the power 3/4 is the trivial bound for L half pi twisted by chi. So chi is modulo m, pi is fixed here. And but you got something like m to the power 3/4 minus 1 by 2000 or something. But anyway, it's a subconvex bound. Right, so I got subconvex bound for the symmetric square L function in the level aspect. And as I mentioned that when you get the symmetric level aspect subconvexity for symmetric square, you were making progress towards the quantum unique ergodicity. So Paul Nelson, he proved that, I mentioned that you need two types of subconvexity bounds for quantum unique ergodicity. You need it for symmetric square, and you need it for symmetric square twisted by G. So I proved it for symmetric square, and then Paul Nelson showed that this also implies subconvexity for symmetric square twisted by G. So we got both of them, and that gives us an effective arithmetic quantum unique ergodicity. And so not only new results, we can also recover the old results that people had proved in the last 100 years. Like we can prove the Burgess bound for GL1 and GL2 in one go. Okay, and so this is something new that we can prove a subwhile bound. So as I mentioned, that Anton Good proved that L half plus IT delta was bounded by T to the power 1/3, and that was a record till recently. And I now have T to the power 1/3 minus delta. So it's just trying to go past what is called the Voronoi barrier. Okay, and more recently, so that this is like last month, I got the T aspect subconvexity for GL2 cross GL3 L function. So when you have a T aspect subconvexity for Rankine-Selberg convolution of GL2 and GL3, that will mean that you get, you get T aspect subconvexity for GL2 because you can take Eisenstein series to be one of them, and you get T aspect subconvexity for GL3 as well, and also for GL1. So when you prove this theorem 7, it gives you T aspect for GL1, GL2, GL3, GL2 cross GL3, all at one go. Okay, and this is the result from last week or the week before, that we have weight aspect subconvexity for symmetric square. L half sin square f is bounded by k to the power half minus some delta, which is reasonably good. And now I have to write this and send this to Paul Nelson, and he'll show that it sim square, it will also give you sim square f twisted by G, and then we'll get the quantum unique ergodicity in the spectral aspect as well. Okay, so this is still a work in progress. All right, thanks for listening.